Alright guys, so let's continue. Okay, let's look at the formula, right? How many cis-trans isomers can be formed basically depends on the number of CC double bond that can exhibit this isomerism. So if M is the number of carbon-carbon double bond that can exhibit, right? Then we basically have this formula 2 to the power of M. All right, so that will be the number of cis-trans isomer that can be formed. Okay, the next major type, right, is actually called enantiomerism. Okay, it refers to a pair of molecules that are actually mirror images of each other. All right, so there's actually 3 requirements for compounds to exhibit enantiomerism. Number 1, presence of a chiral carbon. So what is chiral carbon? Chiral carbon is basically a carbon with 4 different groups of atom bonded to it, or 4 different atoms. Okay, and the second criteria here is actually there must be no plane of symmetry, all right, within the molecule itself. Okay, the third criteria actually not very crucial, because if the first 2 criteria is fulfilled, then the third criteria is almost automatically fulfilled. All right, so let's go on to the quick check here and identify the chiral centers with an asterisk. Okay, so maybe take a pause here, press pause, and try to do for these 3 molecules. All right. Okay, so I'm gonna assume that you have done this quick check. Okay, so for the first molecule, okay, so you have 2 chiral carbon. All right, for the second molecule, okay, how many do we have? Okay, we only have 2. All right, and the last one, actually we don't have any. All right. Okay, so how do you identify the chiral centers, right? Actually pretty straightforward. So I recommend that you basically scan the whole compound. For cyclic structures, right, look for the point of intersection, all right, where there is a substituent. So most likely there will be a chiral there because the H is not shown, right? So if you have a substituent, that's 1, the H, that's 2. Okay, these 2 groups, right, these 2 groups, they will be different because the one on top has a bromine. All right, so if you were to separate it using a dotted line, you will see that this C is different from this C. Okay, therefore there is a chiral here. Okay, the same principle you will apply to get the chiral carbon here. All right, even for non-cyclic compound, you can basically do the same thing. Look for the point where there's a substituent, and very basically you can get 4 different groups. All right, so same thing here. Okay, for the last molecule, the benzene ring, right, all the carbons are basically sp2 hybridized. We'll get to that later, which means that all of them have like sort of a partial double bond. So they will not, as long as you have a double bond, right, you will not have a chiral carbon. All right, so same thing here with a CC double bond O. Okay, this carbon is not chiral because it's bonded to two of the methyl group. Okay, so how do we represent enantiomers, right? After we've found out the chiral center, right? Okay, so we basically just need to place them in a tetrahedral structure, like so, and then draw a mirror plane, and then do the mirror image. All right, literally flip it on the other side. All right, so what's all this solid wedge? It means that the bond is coming out the plane towards you. The dashed line wedge is the bond going into the plane. All right. Okay, so question: can a molecule can it have a chiral carbon and yet not exhibit enantiomerism? Okay, the answer is yes. All right, when it has a plane of symmetry. So an example given to you is right here. Okay, so this molecule cannot exhibit enantiomerism even though it has chiral carbon because it has an internal plane of symmetry. Okay, so enantiomers, right, they have identical physical property except the direction which they rotate plane polarized light. What is plane polarized light? So quite simply, right, plane polarized light is actually this light that has been polarized. Okay, so if you're so interested, okay, so you can look at this diagram. I'm not gonna expound on it because it's really quite silly, right? Plane polarized light. Okay, so light that has passed through polarizer. Okay, next we look at this thing called racemic mixture. This is actually a mixture which contains two enantiomers in equal proportions. All right, and it is optically inactive, as we will call it, because one enantiomer will cancel out the rotation of the other. Okay, so how do we calculate the number of enantiomers? 2 to the power of n, where n is equals to number of chiral carbons.